I'll be teaching to find the density function of z, where z is the minimum of xy divided by the maximum of xy. It is given to us that x and y are independent, identically distributed random variables, where the density function of x is e raised to minus x when x is greater than 0, else it is 0, whereas the density function of y is e raised to minus y when y is greater than 0, else it is 0. So in order to find the density function of z, we first need to find the distribution function of z. But before that, we need to know that for this particular case of z, minimum by maximum, z can have two values. Let's start. So z can be given as the first case when x is greater than equal to y, and the other when x is less than y. So when x is greater than equal to y, substituting in the minimum by maximum case, we can write it as y by x. Whereas when x is less than y, we will write it as x by y. So these are the two values that z can take. So now let us start off by finding the distribution function of z, which is given as fz of z, which is nothing but the probability of z less than equal to small z, which on substituting we get probability of minimum of x comma y divided by the maximum of x comma y less than equal to z. Now, as we had previously stated, that minimum and maximum has two values of z. So f of z will be given as the probability of y by x less than equal to z when x is greater than equal to y, plus the probability of x divided by y less than equal to z when x is less than y. Once further simplifying, it is given as the probability of y less than equal to zx when x is greater than equal to y, plus the probability of x less than equal to zy when x is less than y. Now let us take this as case 1 and this as case 2. We need to plot both these cases on an x and y graph. I have taken the liberty of drawing the x and y graph in advance. So on our xy axis, we plot the line where x is equal to y. So now let's start off with the first condition where x is greater than equal to y, which will lie in the region below the line of x is equal to y, and where y is less than equal to zx will lie in the shaded region which lies below the line of y is equal to zx. So that is the shaded region. Now coming to the second case, when x is less than y, which is the line which lies above the line of x is equal to y. That is this entire region where x is less than equal to zy. That is this shaded region which is on the left hand side of x is equal to zy. So now we need to take a double integration on both these shaded regions. Let's start off with this region first. So the distribution function of z is given as the double integration of the joint density function of x and y, where x goes from 0 to infinity and y goes from 0 to zx. So that would be a dy dx. Plus, now for the second region, that's that one, where we take a double integration of the joint density function of x and y, where y goes from 0 to infinity and x goes from 0 to zy. 0 to zy. Sorry, that's a y. 0 to zy. So that will be a dx dy. Now by using Leibniz formula, we can arrive at the density function of z, which is nothing but the small fz of z, which is nothing but the d by dz of the distribution function of z, which by using Leibniz formula, we get it as 0 to infinity x f of x y x comma zx dx plus 0 to infinity y f of xy zy comma y dy. Now, as it was given to us that x and y are independent, So on further simplifying, we get the density function of z as 0 to infinity x fx of x fy of zx dx plus 0 to infinity y fx of zy fy of y dy. Now, on substituting the values of x, of the density function of x and density function of y, we get it as 0 to infinity x e raised to minus x e raised to minus zx dx plus 0 to infinity y e raised to minus zy e raised to minus y dy. Now on simplifying, 0 to infinity x e raised to minus x 1 plus z dx plus 0 to infinity y e raised to minus y 1 plus z dy. Now by using the identities in integration, we can simplify this equation to be given as 1 upon 1 plus z the whole square plus 1 upon 1 plus z the whole square, which is nothing but 2 upon 1 plus z the whole square. Now this is the density function of z. But now we also need to know the limits of z. Now z is nothing but minimum by maximum. And since the denominator is always maximum, z will always lie in the region of 0 to 1. So this is the range of z, and this is the density function of z. Thank you.